Okay, so we're gonna resume back to we started learning the rules. So we started deriving some rules for rate of change functions. We're gonna resume that in a little while. We're gonna do one more example of the theory behind it. This is really important. Okay. And so let's do one more example of this. So I want to approximate the rate of change of this function g when x equals -1. Okay? And so we know that, so what is the value of h here? What is the value of h that I'm using to do that? Okay, so yeah, I'm using an interval width of 3 because it's starting at 1 up until 4. And then, so I want to estimate the rate of change at 1 using this value h of 3 from 1 to 4. Do it. So estimate the rate of change of g at x equals 1. What'd you get? What's that? -2/3. Okay. So you should have gotten -2/3, or -0.667 is a good approximation for that. Is that what you got? Okay. Review, right? So is that a good? Are we fine with that? The rate of change at 1? Are we good with that? That's a big interval, right? So it's a big interval. How would the actual rate of change at 1 be represented? Is it going to be more negative or less negative? More negative, right? If you imagine a little piece of that black curve as a line, it's heading down more steeply than the purple one. So we're expecting a more negative value. So how do we do that? Yeah, smaller interval. So there you go. There's a smaller interval. Go. So let's get a better estimation for the rate of change of g at 1. What is h for this now? He wants 0.05. Agree with that? Yeah, h is 0.05, and you should get -1.311. Is that right? Around there? Okay. Which is what we thought. More negative than the first approximation based on the pink line. Right? More negative. And so this is going to be pretty close, right? Because if you're just looking at that little segment right there, it's going to be a pretty good representative of the actual rate. Okay, and we're gonna calculate the actual rate and see that it's really close to that soon. Okay, I want you to do the same thing get a good estimation for the rate at 4. So I gave you a new point there. What's the rate of change at 4? that going to be more or less negative than the rate of change at 1? More or less negative? Less, right? It doesn't go down as much for a change in x, right? It doesn't go down as much for a change in x than it does at 1. So we're expecting a lower negative value to be the rate. Go, find it. Okay, we should be getting good at this by now. I got negative 0.33. Is that what you got? Okay. All right. What does the rate of change, r sub g of 4 equals negative 0.33 mean? What does the value negative 0.33 mean? Tell the person next to you. What does that value mean, negative 0.33? Yes, it's the rate of change of the function g at 4. But what does the value mean, negative 0.33? Go. Okay, volunteer. Who can explain? I know Ian knows. Somebody else. Volunteer. You, sir, the blue shirt. Yep.
Okay, so for every change in x, the corresponding change in y is negative 0.33 times the change in x.
Okay, good. If what? If what?
If the value of change in x, or if h is very small.
Okay. And also, yeah, one more thing, and also?
Within the current moment.
Right, at 4. Right, good. Yeah, so it means given any change in x, given any small change in x around 4, right? Given any small change in x around 4, the change in y will be negative 0.33 times that much. So given a small change in x near 4, y will change negative 3.33 times as much as that change in x. You should have said something like that, right? Something like that. Any questions? Okay, so now we want to get these. We want to get these rates exactly. So we want to get the rate of change at 1 exactly and at 4 exactly. In fact, at any x value exactly. Meaning we want a closed form expression to crank out any rate of change for this function g. So I'm going to tell you that the function g is 12 over x plus 2. That's the function we've been working with. 12 over x plus 2. So you see that you get 1 and 4, 4 and 2. Okay. So we want to, what do we want? We want a closed form representation of the rate of change of g at any value of x. How do we begin doing that? How do we begin? How do we begin finding a rate of change function? Right here in the blue hat. Close. What would be here? Yeah. What is it? Yeah. Good. Yeah. G of x plus h minus g of x over h, right? That is our trusted rate of change function. We know we get the change in y over the change in x for that change in x of h, right? And that's going to give us the rate of change. And if h is small enough, that's the exact rate, right? That's the exact rate. Okay, can you set up the first step? So apply the rule of g, like you did in the quiz. You're going to apply the rule of g to the trusted form of the rate of change function. What will the first step be? Go do it. Write it down. get it, sir? Tell me.
12 over x plus h plus 2
Okay.
minus 12 over x plus 2 all over h.
Okay, he said 12 over x plus h plus 2 minus 12 over x plus 2 all over h. Perfect. Right, so we're going to apply the function to g of x plus h. It means whatever g tells us to do with the input, now we're going to do that with x plus h, right? And then whatever g tells us to do with x, we're going to do it with x. And then we set up the ratio. Okay, so now we need to do a little algebra here. So we need to subtract those fractions. To subtract fractions, we need a common denominator. So the common denominator is going to be, in this case, the product of those two. So we're going to multiply those two together. And then how do we get the common denominator in the first fraction? What do we do in the first fraction? Multiply top and bottom by x plus 2. Right? If I multiply the top and bottom by x plus 2 in the first fraction, I get my common denominator. What about in the second fraction? X plus h plus 2. Top and bottom, x plus h plus 2. So I did two steps here. So I multiplied top and bottom of the first one by x plus 2, second one by x plus h plus 2, and then subtracted. So I got my common denominator, 12x plus 2 minus 12 x plus h plus 2. I'm gonna leave that in the numerator, the product there as it is, but I'm gonna simplify out the very top. When you simplify out that whole top, you just end up with 12h. You got 12x and 12x go away, and then 12 times 2 and negative 12 times 2 go away, and all that's left is negative 12h. I knew there was a mistake on this screen. Okay, is that better? There may be another mistake on the screen too. I remember from past semesters. All right, but I think we're good now. We got negative 12h. Okay, now what? See what happens next? H's can go, right? I got an h in the numerator. Of the whole fraction, I have an h in the numerator, and I have an h in the denominator, so those can go. Wait, what?
Well, there's an h in the numerator and denominator, but the numerator is itself a fraction.
That's okay, because we could rewrite that as negative 12 over that denominator all times h. It's the same thing. So that's equivalent to what I have there, right? And then does that make sense? The h's still can go away. H over h. Is it better?
Yeah.
Okay. All right, and
Does the h in the middle,
what?
denominator and numerator, does that h go away as well?
No, that's locked in. It's plus and multiplied, and yeah, no way. So it needs to be h times all this. These are plus, and those are locked in there. So we end up with negative 12 over x plus h plus 2 times x plus 2. And then if we want exact rate of change, what are we looking at? We want h to be really small, essentially 0, right? Essentially 0. So for h essentially 0, we get negative 12 over x plus 2 to the negative 2. Gee whiz, there's the other mistake. Guess I'm catching it on the beginning here. Okay. So that wasn't too bad. It was just a little rough at the beginning. You had to write a lot, but it's not too bad. Questions on that derivation, on the algebra? Are we good? Okay, so what did we just find? What is negative 12 over x plus 2 squared in the big scheme of what we were doing? What does it mean? What's that? Closed form of the rate of change of function g, right? So this is now, and this is exact because it's the expression when h is essentially 0. Okay? So this is our exact rate of change function. in closed form. We like closed form because we can pretty much instantly get any rate of change we want for any x value. We looked at, for x equals 1, what was our approximation? No, we did better than that, right? Negative 1 point something? That was the negative 1.311 or something? Do I have that right? I think I have it on the screen. Yeah, there we go. All right. So when h was 0.05, we calculated negative 1.311. So what is the exact rate of change at 1? Find the exact rate of change at 1. Go. How do you do it? How do you find the exact rate of change at 1? Right here in the flat chart. How do you find the exact rate of change at 1? What? 12 over 3. Sorry. Sorry. Okay, right. So he said plug 1 into this. And you're going to get negative 12 over 9? Or negative 4/3? Is that negative 1.33333? Look at that. So for h is 0.05, we had a pretty darn good approximation. We were off by less than 0.02, right? But here we just can crank it out. Just plug in the 1 and get the exact rate of change. What about for What about for 4? So find the exact rate of change at 4 as well. The negative 12 over 30, is that negative 1/3? Again, very close this time. Off by 0.003333. So off by 1,000, right? Off by 1,000 or 3,000. Okay. So in terms of generating exact rate of change quickly, that's the beauty of a closed form rate of change function, right? So it took us a while just to come up with these two approximations. We had to zoom in, we had to do change in y over change in x, right? But if we have a closed form for the rate of change, we can just pretty much instantly get the rate of change for any x value, right? Any x value. So we like that, right? That's a lot more powerful than having to do all the mechanics. But mechanics are critically important for understanding what's going on, okay? So let's summarize here. All right, so the exact accumulation function is gx, then its exact rate of change function is called the derivative of g. And you've heard this before if you had calculus. So when we've been talking about these exact rate of change functions, the term for that is the derivative of g. Derivative of g. Why? Because we derived it from g. G of x plus h minus g of x over h, right? We derived it from g. But rate of change function is more telling, right? Because it tells us what it is. Derivative, just all it really tells us is we got it from g. Rate of change function tells us that it's rate of change. Okay, so in our example, I have it right here. Negative 12 over x plus 2 squared is the exact rate of change function for that function. And thus, negative 12 over x plus 2 squared is the derivative of g. It's the derivative of g. All right, so there's different notations for the derivative of g, okay, with respect to x. One of them is this. So that's a notation for the exact rate of change function for the function g, or the derivative. Also g prime notation. This is also means the derivative of the exact rate of change function for g. Okay, and we said that this is the definition of it. It's going to be our difference quotient, our trusted form, and then with h essentially 0, or limit as h gets really close to 0. So our notation, r sub g of x, does it mean the derivative? R sub g of x, does that mean the derivative? What did we say? R sub g of x was this thing. Is it the derivative? Maybe, with the condition that h is really small. With the condition that h is really small, our notation is flexible, right? Our notation is flexible. It can mean an approximate rate of change if h is not small, and then it can mean the exact rate is if you add the condition h is really small. Okay. But all of these notations we read as the rate of change of g of x with respect to x. Okay, whether it's this one, g, the prime notation, this notation, or the r sub g of x, they're all of them. We're gonna say it's the rate of change of g of x with respect to x. Okay, that's because that's the most descriptive phrase to use. Okay, but derivative means the same thing. Derivative means the same thing. Okay, any questions on that? Notation and language. Okay, then, so we like these closed forms, so we're going to back to the rules, right? So we want to come up now with as many rules as we can so we can crank out the closed form rate of change functions and have those, because those are the most powerful for cranking out results, right? So here's the 4 that we have so far that we did Tuesday. So the first one we call the power rule, x to the n. X to the n, what was the rate of change function of x to the n, or the derivative of x to the n? N x to the n minus 1. So you can visually, you can think of move the n down to the front as the coefficient, and then reduce the n by 1. Okay? Rate of change of a constant function, 0. Rate of change of a constant times a function. Is that also 0? No. In this case, you just hold on to the constant and multiply it by the rate of change of that other function, g. And then the rate of change of the sum of functions was exactly what we hoped for. The sum of the rates of change, right? So these are the 4 rules that we derived on Tuesday. So now let's practice applying them. And the name of the game here is, when these get harder, is applying rules in combination. So functions will use more than one rule. Okay? For instance, here's a polynomial. In fact, this polynomial uses all 4 rules in combination. So you have to have a roadmap. You have to have a strategy for this. And here's the strategy. Okay? So the strategy is begin by asking, what's the overall structure of it? The overall structure will govern what the overall structure of the derivative is. Okay? So for those of you who have done this before, this is going to seem like overkill, but this strategy is helpful for the harder problems that are coming in the next week. Okay? There's going to be really hard, complicated derivatives coming that are combinations of rules. And so this particular strategy of asking, what's the big picture, what's the overall structure, is going to be really important. So we'll just practice it on this one. So that's my question. Which of the 4 rules, 1, 2, 3, and 4, applies to that whole function as a whole, right? At the overall structure of that, would it be something to a power? Is it the whole thing is a constant? The whole thing is a constant times a function, or the whole thing is a sum? So 1, 2, 3, or 4 is the whole thing. How many people say 1? That function is something to a power. How many say 2? It's a constant. How many people say 3? How many people say 4? Okay, right. Okay. You just didn't say anything, so I didn't know if you were unsure. All right, yeah. So as a whole, that thing is a sum, and so we can start by writing. So the rate of change of capital P equals what? So, and what does the sum rule say? It says that the rate of change of a sum is the sums of the rates of change. So we can write it that way. So P of x here equals the sum of the rate of x to the 11th plus the sum of the rate of negative 5x to the 4th plus the rate at 10x cubed plus the rate of change of 9. So I'm applying that fourth rule. And I'm just doing it out the long way, okay? Just writing out all the steps, okay? So now this first one, the rate of change of x to the 11th, is that a matter of rule 1, 2, 3, or 4? 1, right? X to the 11th. And so that rule tells us that the rate of change of x to the 11th is? Right, you're going to bring the 11 down in front and reduce the exponent by 1. So it would be 11x to the 10th. This next one, negative 5x to the 4th. Is it rule 1, 2, 3, or 4? 1 again. Is it 1 again? Negative 5x to the 4th. The overall structure of that. It's actually not number 1. But it's only one of those rules in terms of its overall structure. It's 3. It's a constant times a function. It's a constant times a function. And then that function is rule number 1, right? So we're going to do, does that make sense? So it's plus, so the rule number 3 says negative 5 times the rate of change of x to the 4th. So negative 5 times the rate of change of x to the 4th, which is, that's rule number 1, 4x cubed. All right, 10x cubed. What number rule is that? Same thing, number 3. It's going to be 10 times the rate of change of x cubed, which is 3x squared. Finally, plus 9. Which of those rules is that one? Number 2. It's a constant. Therefore, 0. Now we can simplify. So the rate of change of P with respect to x is 11x to the 10th minus, and I can multiply there, minus 20x cubed plus 30x squared. So using the trusted form on this would be a nightmare. X plus h to the 11th, right? X plus h to the 4th. Multiplying those out and solving. So this is why we want these fast-tracked rules so that in less than a minute we can write down the exact rate of change function. Okay, questions? Especially those who have never done this before. This is the first time you've seen this. Did you follow it? Yes, please. So rule 3 is if you have a constant times some function, the rate is the constant times the rate of change of the function. Do you follow that? If you have a constant multiplied times some function of x, then its rate of change is that constant times the rate of change of that function. So see.
I guess where did you get the 4x cubed?
Okay, so I'm getting it. Does that make sense, first of all?
Yes.
So do you see that the negative 5x to the 4th is of this form? It's a constant times a function. All right, and so what is the rate of change? It's going to be, we're going to hold on to the constant, negative 5, And then we're going to take the rate of change of what? The function. So what's the rate of change of x to the fourth? Which rule is that?
Oh, so that was using the rule 1.
That's using rule 1. See that? So I did kind of 2 steps at once.
Okay, that was what I was.
I held down to the -5 according to rule 3, and then I also evaluated the rate of change of x to the fourth. Other questions? Yes, please.
Could you skip the second or the third
Yeah,
step?
we could skip a lot of steps. Yeah, but yeah. So this is you're gonna die for these in a week. Okay, this is so easy. So yes. So eventually we're just gonna say, oh, 11x to the 10th, and then think about bringing the 4, -20x cubed. Is that what you're saying? Yeah. Plus 3 times 30x squared plus 0. And we'll just write this all down in one step. But for the first time, I wanted to show you how all the rules apply here. All 4 rules apply. And also emphasize this initial question of what's the overall structure? Because in the harder ones, that's going to be a critical question to answer to get started correctly. What's the overall structure of the function? That's going to govern the derivative rule that we're going to use in totality to do that rate of change function. But yes, this one, after practicing these, you should just be able to write that down in one step. Other questions? Okay, so we already did that. So now that we have this rate of change function, we have the rate of change of p. Is that the same function we just did? Yeah, so we have the rate of change of p. So given that, let's just do that first one first. I want you to describe the meaning of this expression, okay? And then write it in closed form. So describe the meaning of this expression to the person next to you, and then work together to write that expression in closed form. Go.
Up to 2. So it'd be the accumulation from 2. Yeah, I missed it. I still thought this was. The other one's just but it was writing the.
see how it went. So, all right. So here in the plaid shirt, the red plaid shirt right here. How did part A go? What is the meaning of that function z of x? Starting at x equals 2, okay. So it's a net accumulation starting at x equals 2. When? There's one more detail. What else? What's the last thing we could do to describe this? Yes, sir.
H is very small.
Yeah, that's true. Okay, yeah, that's true. What else do we have from that expression that we know about this net accumulation? Yeah, good. So when the rate of change is this thing. So you should have said something like that. This is a net accumulation function starting at x equals 2 or zeroed out at x equals 2 when the rate of change is that. Okay? So now we want to write this in closed form. So what is it the same as? It's the same as, so getting the net accumulation little by little starting at x equals 2 up to x is the same as what? What is that the same as? It allows us to write it in closed form. Number from Tuesday, yeah.
Z of x minus d of 2.
No, not quite. Not z of x minus z of 2. Okay, p of x minus p of 2. So p of x minus p of 2. Is that right? And if so, why? Is it right? Yes, why?
Because z of x is a closed form, so you can't just plug numbers into that and get results.
Okay. Yeah, so p is our amount function that has this rate, right? If p is the amount function from where this rate came from. We should recognize that rate came from the function p. So p is like an amount function that has that rate of change. And so if we want the net accumulation from 2 to x, what would this be? This would be the what? Total change in p from what? 2 to x. And if that's the rate of change of p, are these two things the same? The net accumulation from 2 to x and the total change in p from 2 to x? Are they the same? Yeah, because that's the rate of change of p. So this is the amount function that has that rate. So it's the total change in amount is the same as the accumulation from 2 to x at its rate of change, right? At its rate of change. So yes, it is. So then we could actually write the closed form. Then what is the closed form for this integral? Somebody knew. So then I want to write out a closed form expression for that z of x function. What would it be? Anybody? Yes, sir. X to the 11th. Right? Right? Uh-huh. Uh-huh. And we could simplify all that. So p of 2 is some number, and we could just have that one number. But yes, that's it, right? So there's a closed form expression, closed version of z of x. They both give the amount of change in p starting at 2 and ending at x. One gives it according to the rate, thinking thinking of it as little bits of change all the way from 2 to x, and then 1 gives it as total change from final value minus initial value, right? Final value p minus initial value p. And this is our closed form then for that. Again, all this could be simplified into a single value, right? So we're just not going to take the time to do it. But all that is just a number, right? All that's just a number. Does it make sense? Any questions? All right, super important. That's really important. Last chance. Any questions? All right, how about this one? Do it again. Go. Q of x. What's the meaning of Q of x? Can you write a closed form expression for Q of x? Okay, let's see how we did. How about in the blue and black collared shirt right there? How'd you do? Okay, right. So it's a net accumulation starting at -1 to x when the rate is 30t squared. Okay, and now I want to write a closed form representation of that. I want that in closed form. How about here in the green shirt, the young lady, the dark green shirt? Yeah, did you get the closed form for this? Okay, almost. It's going to be 30, what? Not t squared. X squared. Okay. Got the right idea, is that right? So is the net accumulation the difference of the rate of change? So what should it be? So yeah, so we got the kind of the right structure, we got the right overall form, but we're not going to use the rate of change function here, right? We need an amount function that has that as its rate. Yes, sir. 10x cubed minus what? Someone else had their hand raised. Is that what you're going to say? Yeah. So we need the amount function whose rate is 30t squared. Well, that was part of p, right? Part of p we had 10x cubed was a little part of that rate, and the amount for that was, oh sorry, yeah. So 10x cubed was a little part of p that gave us that rate 30x squared, 30t squared. Okay, so does this make sense? So closed form, 10x cubed, what, plus, is that plus 10? Yeah, plus 10. So we got a closed form accumulation function. We got qx in closed form, whereas before, when we were doing test 2 stuff, we had to stop there. But now that we're working on rate of change functions, we have the amount function that has this rate, and so we need what it turns out to be the total change in the amount from -1 to x is 10x cubed plus 10. 10x cubed minus 10 to the minus 1 cubed. Does it make sense? Anybody have a question? Yes, please.
So if you change a from -1 to something else, just the second half of the equation.
Yeah, so if you want the accumulation now starting, wait, so what does it mean? It's the net accumulation from -1 to x. So this is going to be the total change in the amount from -1 to x. So if I started some other value, say 4, then I need the total change in the amount from 4 to x, and that's going to be 10 times 4 cubed. Other questions? There we go. All right, so let's do another rule. A couple more rules here. Rate of change of the square root function. Okay, I want to find the rate of change of the square root function. Write down the first step. If I want to figure out what the rate of change of the square root function is, what's the first step? Write it down. That's the first step. How about in the green shirt? Did you get it? Tell me. Okay, so just literally as square root of x, and we want to derive it. What would the first thing we would do be? Literally as square root of x if we want to derive. So we're gonna do that later, but right, trusted form, right? Trusted form. So trusted form is going to be f of x plus h minus f of x all over h. Okay, don't write this down. You can check it out in the video or take notes later. But so first of all, from algebra, remember that a minus b times a plus b was a squared minus b squared. So to chisel at this algebraically, we're going to use that. So we're going to multiply the top and the bottom by the sum. Right? We have a difference. We're going to multiply by the sum. Like that. Okay? So because I'm looking in the numerator to use this algebra, this fact from algebra, right? And so what will the numerator become? A squared minus b squared. It'll just be x plus h minus x, right? If I square the a and square the b. So it's just going to be square root of x plus h squared, which is x plus h, minus square root of x squared, which is x. All times the new denominator. And so then I get h in the top, and I have an h in the bottom. And I get 1 over square root of x plus h plus x, and then when h is small, I get 1 over square root of x plus square root of x, or 1 over 2 square root of x. So there's the algebra for that one. So we got another rule, okay? But what she said was square root of x can also be thought of as x to the 1/2, right? So we can take x to the 1/2 and apply a rule we already know, which is the power rule, right? What will the power rule be on x to the 1/2? 1/2 x to the, literally you subtract 1 from the exponent no matter what it was to start with. Positive, negative, fraction, whatever. You always just subtract 1. So you get 1/2 x to the negative 1/2. So is that the same as what we got deriving it the long way? Yeah, we got a 1/2, and then x to the minus 1/2 is 1 over square root of x. Okay? So we did the long way. We got 1 over 2 square root of x. Then we notice that the power was 1/2. Applied the power rule, get the same thing. 1/2 square root of x. Okay. We got 5 rules now. We got 5. So this is what? This is the rate of change, exact rate of change function in closed form when our function is, our accumulation or amount function is square root of x. All right, exponential functions. I'm not going to derive this one. I'm just going to tell you what it is, okay? Exponential functions. Any constant base b to the x turns out to be the rate of change function. In fact, it's b to the x again times some constant, and that constant turns out to be the natural log of the base, natural log of b. Okay, then there's a special one of these. Okay, e is the natural base, and that's the special case when that value of k, or natural log of e, is equal to 1. So we have this function, that the rate of change of e to the x is itself e to the x. It's a really special function, that the value of the amount is the same as the rate at any value of x. We're going to skip that for now. All right, so 3 more rules. We had the 4 from before. We got 3 more. We got square root of x is, the rate of change function is 1/2 square root of x. An exponential function is, the rate of change of b to the x is b to the x times natural log of b. And you can put the natural log before or after, it doesn't matter. But then a special case of that is e to the x, where the natural log of e is 1. So the rate of change of e to the x is also e to the x. Really special function, right? The rate of change is the same as the y value. The rate of change of the function is the same as the amount, or the y value. All right, so quick. Try one more. Go. Do this before we leave. All right. Okay. 4 times, what's the rate of change? So it's going to be 4 times the rate of change of that. That's the constant multiple rule, right? It's going to be 4 times the rate of change of what's in parentheses. What's the rate of change of what's in parentheses? Well, that's the sum rule. So we're going to do the rate of change of a to the x plus x to the minus c. Rate of change of a to the x is a to the x ln of 8 plus rate of change of x to the minus 8. Negative 8 x to the minus 9 plus the rate of change of x. Rate of change of x is 1. So you could think of it as x to the 1, or you could just think of the function x has what rate of change? Has a constant rate of change of 1. Okay? Minus 2e to the x. So minus 2 times the rate of change of e to the x. Just e to the x, we said. Plus the rate of change of x times x to the 10.7. 10.7, x to the 9.7. That's the power rule. Minus rate of change of radical x. 1 over 2 squared of x. Minus e squared. Okay, careful. So, students throughout the ages have tried to write that the rate of change was e squared or 2e. It's neither. That's a number. That's a constant. That's a constant. So just 0. So there it is. That's the rate of change of p with respect to x. Okay, if you're signed up to take the research thing tonight, don't forget. Show up. Thanks.
Count 271. Yeah. How does that compare to something like this? Where do we go from here?
Calc 2 is kind of more of a topics course. So there's a lot of stuff with integrals and accumulation functions.
Okay.
So you do like a bunch of geometry, you do physics problems,
Sort of
areas.
applied
Yeah, there's a
calc
lot of applications of accumulation functions and integral functions, and then there's sequences and series, which is a whole different, like the sum stuff, like infinite sums. You do that. You also do polar coordinates and parametric functions, and parametric functions are like really important in Calc 3. It's a different way to organize a function. It's called parametric functions. So it's kind of more of a topics course, whereas this kind of has it's kind of one journey kind of.
Yeah.
So, are you taking it in the summer, or are you?
Yeah, I'm doing that in summer, and then I'll do Calc 3 in the fall. So I changed my minor, so that's why
Okay.
they required it. So kind of.
Okay, cool. Are you in my Calc 3 then?
I think I originally signed up for your Calc 3, but it didn't hash out. I got to double check and see who the professor is. I tried to sign up,
Okay.
but
Your schedule didn't work out.
yeah, there's some other classes that I needed that were in that time. So.
Got it. Okay. Cool. Very good. It's in Wexler, basement 21.
So what we take the test?
Yeah. So you take the test. Yeah. So and you can just I think it's between 4 and 7.
Yeah, because my class signs at 5. So
Perfect. Okay. And then you'll fill out there's some kind of release or waiver form or something like that. You just fill that out there.
okay. Yeah. All right. Thank you.
You're welcome. Hey. Sure.
So do you prove this that this is a total accumulation graph or this is a net accumulation graph?
Sure.
So
Well, so yeah, if net accumulation for that would be this one, right? 0 to x of rt dt. Right? But
and then if it was a total accumulation, you would add all the values
then this you would add all if this is this
like if this value was like 5 or something.
yeah, f of right, so it would be whatever that
F of 0.
or if that was 5, right, it'd be 5 plus that.
Well, this would be the total accumulation, wouldn't it be? Just this. Because
The whole thing now is total accumulation.
Right. So without that, it's net
Net accumulation, that's right.
So on the quiz,
Yeah.
this is accumulation.
No, but you're representing C. See, use this fact to represent C in open form. So this, the net accumulation starting at -4 is not the function C unless you take all the accumulation from before as well. You're
Well, we're just looking at net accumulation.
no, you're representing C. Represent C. You have to be representing the function C, not the net accumulation. So it's not asking for the net accumulation starting at -4. It's asking for to rewrite C, like in the practice quiz. You did that practice quiz too, right? So now you're rewriting the function C. And so if you're going to do the net accumulation starting at -4, to get C, you gotta also. Does that make sense? Is that better? It's not asking for a net accumulation function. It's asking you to represent C in open form, which means net accumulation plus all the accumulation before gives you C.